look at the way energy affects the outcome of a downhill race. So we're going to race some things downhill, like that hot car, and see what that has to do with energy. You know, energy, the total energy, let's just look at this little car. When it goes downhill, first of all, it starts with potential energy, mgh, mass times gravity times the height at which it started. So it goes from here to here, and so what changes? H changes. It also moves in a straight line. So that's 1/2 mv squared. That's our kinetic energy. And there's something else. The wheels spin, and that's rotational energy. So that's 1/2 I squared omega squared. These are terms you might not be familiar with, but I is kind of like mass, except it's how hard it is to turn something. And the omega squared is just the rotational speed, how many radians per second. So let's have a look at a race here and see if you can predict the outcome, because sometimes it's surprising. For example, let's try to look at the difference in, I wonder who's going to win this race. We have this hoop and we have a ball. And I know that they are different weights, and I think you just have to assume that weight is not going to be a factor. But now who's going to win? Watch again. It looks like the ball wins. I wonder why that is. They both started with the same mgh. They both started with the same potential energy. But then and so this is the energy that they had at the beginning. So it had to be divided between kinetic energy and rotational energy. So which one had to put more into rotation? Well, see, it's that I factor. The hoop has a higher I. It has a larger moment of inertia because all of its mass is at the outside, where with the ball, the mass is more concentrated. So if we go like this, again, the ball always wins. Now, can you predict who would win between, say, the ball and the car? Remember, the ball was our previous winner. So we have a car here, and we have a ball here. Are you ready? The car wins. The car wins. Now, why is that? Well, let's look at this carefully. They both started with this being the same. But once they got going, they had to divide this energy up between straight line speed and rotation. The ball, all of it had to go into rotation, like the whole ball has to spin. So as a result, it uses up a lot of its energy just to rotate. With the car, these tiny little wheels have hardly any rotational energy. So all of its energy can go into winning the race. But there's other factors too. Let's look at these two identical wheels. Look at them. Well, they're not identical. One's blue and one's red. And you could ask me, are there any other things that are different about them? Well, there are, but I'm not going to tell you what. I can tell you they're made of the same materials. They have the same weight. They're the same width. Everything about them is the same except for one thing. And that one thing definitely will affect the outcome of a race. Ready? Go. The red one won. Let's try it again. The red one wins again. I wonder why that is. I wonder why. It's certainly, this might give you a clue, because let's have a look at how fast this one goes. Oh, there's something, by the way, this is like these. This has the same weight, same dimensions, same materials. So there's something about these that's different. And remember, the red one was the winner, and let's look at it. I hope you can see this, but the red one, those kind of dark spots, that's lead. So these wheels are aluminum. And so for the red one, the weight was concentrated in the middle. And for the blue one, the weight was concentrated on the outside. So when the weight is on the outside, it makes the moment of inertia, or the I, very large. So it has less energy to go into velocity. And for the other one, it's the opposite. Now, to really make it ridiculously obvious, I'm going to race this thing all by itself. This is a wheel and axle. It's a wheel with an axle on it. So you can see it from here. You see a very small axle, very big wheel, and we're going to have the same hill here, and we'll see how fast this races down the hill. Now it's blinding speed, so watch out. Oh, there it goes. Oh, I'm going to balance it a little bit better. And you see it just creeps down the hill because almost all of its energy goes into rotation. Very little is left over for translation. And of course, it started off with a fixed amount of potential energy, which went down to zero, from here down to here to zero. And that potential energy was divided up between these two. And that's how energy makes a difference to how fast things go downhill. Maybe you can try some of these yourself.